This is the 9th video on inverse Laplace. We're going to look at solving ODEs with Laplace, and in particular, the purpose of this video is tutorial examples. We're going to assume then that students are competent in inverse Laplace techniques for arbitrary Laplace transforms. And the purpose of this video is to give some tutorial type examples which students can work on, but then what we'll do is we'll show the derivation of the solutions so students can check their work later. First two examples then. You'll notice we've got two ODEs here. dx dt plus 0.2x equals 4e to the minus 0.5t, and dy dt plus 2y equals 1 plus 0.4 cos t. Now, what we want you to do is pause the video now and try these by yourself. Only once you've had a good attempt at these should you press continue and look at the solutions that we're going to give. I'm going to continue now. First one then, dx dt plus 0.2x equals 4e to the minus 0.5t. The first thing then to do is to take Laplace. So if I take Laplace, and I'm going to skip some of the steps because you should be familiar with this by now, and I've made a silly mistake to start. So we've got s, x of s, plus 0.2 x of s equals 4 into 1 over s plus 0.5, and what I've done is I've assumed, because we're doing Laplace type methods, that x of 0 equals 0. So I've taken Laplace of the left hand side and Laplace of the right hand side. Now what I can do is rearrange this to find x of s. So I'm going to get x of s equals 4 over s plus 0.5 times s plus 0.2. And if I put this into partial fractions, you'll see I get a over s plus 0.5 plus b over s plus 0.2. Now what I can do next is use the cover-up rule. So first of all, if we set s equal to minus 0.5, then I'll write it over here. I'll use red, so s equals minus 0.5 in the cover-up rule. Then the bit I'm looking at is this bit which I'm just circling in red here. I'm putting s equal minus 0.5 into there. And what you will see is this gives you minus 4 over 0.3 divided by s plus 0.5. Next, I use black. I'm going to set s equal to minus 0.2, and if I do that, I'm going to be using this bit, which I'm just circling in black now. So what you're going to get is plus 4 over 0.3 over s plus 0.2. Hopefully the rest of the inverse Laplace is by inspection. You'll see the two terms I've got at the bottom are simple exponentials, e to the minus 0.5t, e to the minus 0.2t, and obviously the numerators tell us how much you multiply the exponential by. Next example then, dy dt plus 2y equals 1 plus 0.4 cos t. So again, I'm going to take Laplace. So I've got s plus 2 into y of s equals 1 over s, and that's Laplace of 1, plus 0.4s over s squared plus 1, which is the Laplace of 0.4 cos t. Now if I rearrange this, I'm going to get y of s equals 1 over s plus 2 plus 0.4s over s plus 2 s squared plus 1. Now you'll notice I haven't combined the two terms on the right hand side because that would give me a fourth order denominator, which would make things more complex. So I've decided it's actually easier to do partial fractions for each of these bits in turn. So this one over here is going to come as a over s plus b over s plus 2. If I use the cover-up rule, I set s equal to 0, I will get a half, so a is a half. So I've got 0.5 over s, and then minus 0.5 over s plus 2. So that's that bit on the left. Now what about this bit here? This bit is going to come as c over s plus 2 plus ds over s squared plus 1 plus e over s squared plus 1. And you'll remember what we've done is we've separated it into a sine, and a cosine. So the e over s squared plus 1 will give me a sine, and the d s over s squared plus 1 will give me a cosine, and the other term gives me another e to the minus 2t. Now, I can use a cover-up rule to get capital C. So what we do is we set s equal to minus 2 and see what we've got left in this function. So we've got 0.4s over s squared plus 1. If s equals minus 2, then what you're going to get is minus 0.8 over 5. And if I just do a little blob over here, so if you wanted to work that out, that's going to be minus 0.16. I might need that in a minute. Okay. Now, in order to do the other bit, I'm going to need to multiply up top and bottom. You'll remember when you've got these sinusoids, it tends to be that you have to do an expansion. So when I do an expansion, I'm going to get 0.4s equals c into s squared plus 1 plus ds plus e into s plus 2. Okay, so that's the expansion technique, which we've covered in earlier videos. Now what I can do is things like, let's equate coefficients of s squared. So you're going to get 0 equals c plus d, which tells you that d equals plus 0.16, because c is minus 0.16. What can I do next is I can look, for example, at the constants, in which case I'm going to get 0 equals c plus 2e, which tells you that e equals 0.32. Sorry, I've got that back to front. That always happens when you're doing something. E equals 2e. It means e equals 0.08. So I've now finished all the difficult parts of this inverse Laplace. You can now put the numbers in. So if I want to do that, I can cross this e and put 0.08. I can cross this d, put 0.16. I can cross this c and put minus 0.16, and then inverse Laplace is by inspection. So I'll circle all the terms you've got in case you've forgotten. You've got this term down here, which gives you a 0.5. You've got this term here, which gives you a minus 0.5 e to the minus 2t. You've got this term here, which gives you a minus 0.16 e to the minus 2t, and you'll notice there's two terms with e to the minus 2t, so you can add those together. You've got this term here, which gives you a 0.16 cos t, and you've got this term here, which gives you a 0.08 sin t. Example 2 then. Now we're making the examples just a little bit more complicated. Use Laplace to solve the following pair of equations, and you'll notice this pair of equations represent a feedback loop with PI control. So first we'll take Laplace of each of the equations in turn. So I'm going to get s minus 2 into w equals 5u. That's from that one. Hopefully that was straightforward. And then over here I'm going to get u equals 0.2 plus 0.1 over s. You'll remember the Laplace of an integral, you multiply by 1 over s. And then I'm going to have to do Laplace of 1, which is 1 over s, and Laplace of w, capital W. Now, what I'm going to do is take this u and put it in here. So what we get is s minus 2w equals 5. I'm going to multiply this up by s just for convenience. 0.2s plus 0.1 divided by s into 1 over s minus w. Now, What I can do is I can multiply both sides by s. So if I cross that s there and put another s there, it just makes life a little bit easier. And next I'm going to bring all the w's across to the same side. So I've got s squared minus 2s plus s plus 0.5 into w equals s plus 0.5 into 1 over s. So you'll notice the w over here had a minus sign on, so when I bring it across to the other side, the coefficients come as plus. Now I can simplify this expression here to give myself s squared minus s plus 0.5. So what I'm going to do, if you just make sure you've got a screen capture in your mind of this page, I'm going to consolidate this on the next slide so we can see what we've got all together. So now what have we got? We've got w equals, and we had s plus 0.5 divided by s squared minus s plus 0.5 times s. So we've taken these two differential equations by doing Laplace transforms and joining terms. We've ended up with a relatively simple expression for w. Now what I've got to do next is say, okay, what forms in the table does this represent? And you'll notice this denominator factor, the quadratic factor, represents something with complex roots, sine and cosine. So I'm going to put down what you've actually got. You've got w equals s plus 0.5, and if you put it into this quadratic factor rule, you've actually got s minus 0.5 squared plus 0.5 squared. There's your classic exponential times sine and cosine form. So finally, having got into the requisite form, I can now do partial fractions. I'm going to get w equals a into s minus 0.5, so that will be the cosine term, plus b times 0.5, that's the sine term, and that will be all over s minus 0.5 squared plus 0.5 squared, and then plus c over s. So you'll see I've used the standard trick of writing the partial fractions in the form that I expect I will get from my table. So the a times s minus 0.5 tells me what I'm expecting to get the exponential times cos, and the b times 0.5 tells me about exponential times sine. Okay, I can use the cover-up rule to get c. So if we do that, if we write cover-up rule, then you'll see if I set s equal to 0, then c equals 0.5 over 0.5, and what that gives me is 1. So c equals 1. Now I'm going to move to the next page. So the next thing I'm going to do is multiply up both sides by the denominator to do the expansion rule. So just make sure you can see what's on this page before we do that. Okay, here we go then. So multiplying up both sides, we get s plus 0.5 equals a times s minus 0.5 plus b s times 0.5 plus c into, and then that was your quadratic term, your s squared minus s plus 0.5. Now, I already know that c equals 1, but let's do coefficients of s squared. You're going to get 0 equals a plus c. So that gives me a equals minus 1, because I know c equals 1. Next, let's do coefficients of s. So I'm going to get 1 equals minus a over 2 plus b over 2 minus c. So if I rearrange that, I get 1 plus c plus a over 2 times 2 equals b which equals 3. So if you then pull back what you had on the previous page, just to check what everything related to, you'll see that the final answer is going to be W equals C, which is 1, and then he had A, e to the minus 0.5t cos t, and A is a minus 1, so you've got minus e to the minus 0.5, sorry, it's plus, get it right, e to the plus 0.5t times cos of 0.5t, and then you had plus 3 e to the 0.5t sine 0.5t. Final example then. Purpose of this example is to show how you might handle systems in series. So you'll see I've got a differential equation involving x and some input 3, and then a differential equation with z where z depends upon x, and a differential equation with y where y depends on z. So in essence the solution for x goes in to give you z, the solution for z goes in to give you y. So we'll look at how we might do this. Again, a reminder, pause the video before you carry on so you can try it yourself before you look at the solution. Here's the 3 equations again then. So first of all, as ever, I'm just going to take Laplace of each in turn. So with the top one, I've got x equals 3 over s, so that's Laplace of 3 is 3 over s. And then from the differential bit, I've got s squared plus 4s plus 3. What about this z term then? Well, with z, you'll notice on the top I've got 4s plus 5 into x, and then the differential on the bottom I've got s squared plus 0.2s plus 1.01, and then finally for y I've got z over 3s plus 6. Now you remember what we've just said. I can take the x from here and put it in here. I can take the z from here and put it in here. So what I'm going to end up with is y equals, and this is going to be quite a long expression, 3 into 4s plus 5 divided by 3s plus 6, s squared plus 0.2s plus 1.01, and then there's an s, and then there's an s squared plus 4s plus 3. Now, you might not be able to see this by inspection, but just a note for you. This quadratic here is going to become s plus 0.1 squared plus 1 squared, so that gives you the exponential times sinusoid type of term. This quadratic here comes as s plus 1, s plus 3. So you can indeed expand this out, but what do you notice? You've got 6 poles in this denominator, and that means that the partial fractions is going to be very messy indeed. And you might be saying, do I really want to be doing this on pen and paper? And the answer is probably not. So while you can do it, what I would suggest is by the time you've got it to this stage, probably you need to be going to a piece of computer software. So that's what we're going to do next. I'll just find MATLAB, so there it is. So first of all, I'm going to enter x. So there's the expression for x. You can see 3 over s times s squared plus 4s plus 3. That's x entered. Now I'm going to enter z. So there's z. You can see it's 4s plus 5 over s squared plus 0.2s plus 1.01 all times x. So there's z defined. It's beginning to look a bit messy. And finally, I'm going to enter y. There it is, 1 over 3s plus 6 times z. There's y beginning to go off the screen, looking rather horrible. If I now want the inverse Laplace, I can use the MATLAB command iLaplace y, and there's your answer. And you'll notice, okay, it scrolls across the screen a bit. I'm not too worried about that because this is just an illustration. So a summary. We've demonstrated that Laplace can be used to solve simple ODEs. We've given some tutorial questions that you can try by yourselves, and then we've gone through the work solutions in real time so that you can check what you've done against a sort of almost ideal solution, albeit we're working on a screen so we can't be as tidy as you could be on a piece of paper. And a reminder that once the numbers start getting complex, like with the 6th order example, I really would ask the question why you're doing it on pen and paper. Ultimately, you should be reverting to a computer because that will be far more efficient.